So dark matter is extremely important in forming the very large scale in the galactic scale, the structure in the galactic scale. And it's also essential to explain the observations at the galactic scale and above. However, we have not been able to detect dark matter on Earth experiments. So my research focused on understanding dark matter, the nature of dark matter. Is there any interaction beyond gravity? And also, how can we detect dark matter and other theoretically motivated elusive particles and understand their properties? So today, I will tell you my unique combination of theoretical expertise and experimental involvement and development. And furthermore, I will tell you my short-term focus plan and also the long-term vision. So the short-term focus plan focus on the intensity frontier. By intensity, I mean that, for example, I have a fixed target. I have very intense particle beam colliding the fixed target. And this way, I can produce the most elusive weakly interacting particle on the other side to be detected by a well-designed detectors. So this program has been very successful. In fact, one of these experiments actually found neutrino in Los Alamos, where I'm currently working at. So it's very exciting to continue this program. And my research bringing a lot of new ideas on how to analyze the data from neutrino experiments to study the traces of dark matter and other theoretically motivated models. So I studied several of these very exciting models, study their signature, and then this series of neutrino experiments actually take into account my suggestion and conduct their analysis. For example, for several of the models that I studied. And in particular, with collaborating with microboom experiments, we are actually having an exciting update on such one of these analysis of a well-motivated dark matter model that can have impact on astrophysics and cosmology. And this result is actually going to be released soon. So it's a very exciting time. And the analysis that we conduct can inform a lot of the follow-up series of neutrino experiment at Fermilab in the US, and also the large-scale experiment like DUIN in the US and HyperK in Japan. So what we do now is extremely timely because it will tell us how we can optimize the experiments, these very large-scale experiment, and how we can do analysis with this experiment. So it's extremely timely. Furthermore, equally excitingly, I have proposed my own small-scale experiment, actually several of them also in US, Japan, and also in Europe, in Switzerland. So the one in Switzerland is called Formosa, which is a dedicated experiment using the high energy and high intensity collision of the Large Hadron Collider. So the exciting new thing is we have both the high energy collision and high intensity collision. So it's at the forefront of high energy and high intensity frontier. And this way we can produce the most elusive particle and also heavier ones that can be detected downstream by the Formosa experiment. And Formosa can help probe a very important parameter space, again, that is very important for astrophysics and cosmology and for particle physics. And it's also, this parameter is also motivated by high energy theory like string theory and grand unification theory. So this signature is extremely exciting and we should do it now. And actually, because Formosa, we actually got funded to build a prototype and we actually completed the prototype. That's the second update. We're analyzing the data so it will inform us the future Formosa, full Formosa design, which is a very exciting, timely work. So in summary, in the first 3 to 4 years, I will focus on theoretical development, particle production, and analyzing the existing data. The middle 3 years, I will focus on studying more upcoming data and also help further develop Formosa and also other related studies. And the final 2 years, it will depend on what happened in the first 6 to 7 years. I will design my program based on that. But I also told you I have the long-term vision. I already published a series of papers on how to use quantum sensor, space mission, planetary data. The space mission include a future mission like OSIRIS-REx mission. We can actually study dark matter even gravitationally in the solar system when there is overdensity. So some of these overdensity can be probed with this program. So it's a very exciting but long-term program. So in summary, combining my theoretical expertise and experimental involvement, the Dorothy Hodgkins Fellowship can provide me with a stable platform to focus on finishing this very important timely work and also develop my long-term vision. Thank you. 多久？